Testing, can you hear me? Testing, can you hear me? Um, this video is unlisted right now. I haven't made it public yet. Hello, everyone. Can you hear me? Uh, so I'm going to be reading the Discrete math book again. I'm just going to be reading the next chapter from where I left off last time. So last time I was reading about graph theory. Well, I just started on graph theory. They define what graph theory is from what I remember. So graph theory is like vertices and edges that connect them. And a graph is defined with an ordered pair, V and E. And then these are the vertices. Vertices is a set of labels. So A, B, C. So each vertices has a label, A, B, and C. And then edges is like a set of ordered pairs which connect the vertices. So edges is, we have a set here. So we have AB, AC, and then CB. Then maybe we could have point D as well. D, which is connected by A and let's say B. So we have AD and then BD. So this is an example of a graph. And I think edges cannot be repeated twice. So AD can only be connected once. You cannot have like AB once and then AB twice again. But they in the example they gave, the bridge example, they were like these 7 bridges. This island is one vertex, this island is one vertex, this line is one vertex, this line is one vertex. The connection from this vertex to this vertex has 2 edges. So that means we to represent this as a graph, we need something called a multiset. Because set doesn't allow multiple elements. Multisets, well, the order doesn't matter, but it also allows multiple elements. So we have AB, and if we want AB twice, we can have a multiset. Edges could be a multiset with AB repeating twice. Sorry. Ordered pair. Maybe. Wait, is it ordered pair or is it set of sets? That I can't remember. Hold on. No, it's a set of sets. It's not ordered pair. Ordered only this is ordered pair. Yeah, the outer part is ordered pair, the rest is like set of sets. This is wrong. This is going to take time. So we have this, right? Set of sets. Do we define like is the notation for multi-set the same way? Like the same as set? They also talked about isomorphic. We'll get on that later. Subgraph, induced subgraph. Where is the multi-set thingy? Multi-set. A multi-set is a set in which we are allowed to include a single element multiple times. How do you define it? This is a degree sequence. Okay, they don't really go into the notation for multisets, I don't think. And they also talked about what was it? Edges, graphs. Yeah, isomorphic. It's I have isomorphism between two graphs, the bijection between the vertices of the graph such that AB is an edge in G1 if and only if A if B is an edge in G2. Okay, so for what I understand, if you have a graph, any graph, like let's say A, B, like this one over here, and you have a completely different graph with different vertices, like let's say U, V, W, Z. Isomorphic graph is like you can have a function that goes from U to A and then creates this same graph. For example, it's like this. If it's like this, I can have a function that assigns U to A, V to B, W to C, and Z to D, and I will get this graphs. That means if I have a one-to-one function that can assign these vertices to these vertices and get the same graph, then the graphs are isomorphic. In other words, they just look the same. You can like, yeah, the graph just looks the same. That's how I understand it. Well, not exactly look the same, but you can make them look the same with the vertices and edges given. So we have this graph. So if we have something like alpha, beta, um, delta is like this, right? And then let's say epsilon. We have this u, yeah, so alpha. Suppose uh, and then this part goes to, and then these. Yeah, this and this was also isomorphic with these two because like you can rearrange the vertices and edges to make them look like exactly like these graphs. And yeah, you can assign like u to alpha, v to beta, w to What is it? Epsilon z to delta. And then like get this graph back. They also talked about subgraphs and induced subgraph. The subgraph is like G2 is a subgraph of G1 because G2 exists in G1. G4 is not a subgraph because like you see there's F connecting to E and then E connecting to C. Over here, F directly connects to C. There's no vertex E. There's no edge that connects F to C, but there is an edge in G4 that connects F to C. So G4 is not a subgraph. G3 is something called an induced subgraph. It's a subgraph, but it's a specific subgraph called induced subgraph. So induced subgraph have like some edges missing as well. So in G2 with A, B, C, D over here and A, B, C, D over here, all the edges are there with A, B, C, D. But with G3, if you just look at A, B, C, D, one of the A, B edge is missing. So G3 is a subgraph of G1, but because some of the edges are also missing, then it's an induced subgraph. Uh, Connected, the graph above are also connected. You can get from any vertex to any other vertex by following some path or edge. Okay, so this graph over here is not connected because A and B are not connected. Also, they said that the degree of vertices is twice the edges, but that makes sense if you take this graph. The degree of the vertices, like how many edges are poking out of the vertex. So A has 1, 2, 3, C has 1, 2, B has 1, 2, 3, and D has 1, 2. But if you count the number of edges, when we are counting the degrees, the edge coming out of A and the edge coming out of B is the same edge. So the edges get counted twice. So the number of degrees, number of total degrees for all vertices, the sum of them is twice the edges. Yeah. We have a number of edges, but when we count the degrees, we count twice the edges because we are counting the edges twice. The one with one vertex and one with the adjacent vertex. Yeah, let's just go to trees. Find a subgraph with the smallest number of edges that is still connected and contains all the vertices. Can I copy the image? Oh no, I can't. But I can redraw it right. Like that. So this, wait, I should use a different color. This, and this. These are the vertices. The question is, I need to create a subgraph with the smallest number of edges that is still connected and contains all the vertices. So I guess I can start here, connect these two, connect these two, connect these, connect this. One, two, three, four, five, six edges. There are 1, 2, 3, 4, 5, 6, 7 vertices. So yeah, we need a minimum of 6, right? To connect all of them. Otherwise, one vertex will be left out. Find a subgraph with the largest number of edges that doesn't contain any cycle. Yes, cutting off this. Hold on. Yeah, so We can, here is a cycle. So we can cut off that. So we can cut off that. We can cut this off. Like we can cut this off and then 1, 2, 3, 4, 5, 6. They said find a subgraph with the largest number of edges that doesn't contain any cycles. How about this? This 1, 2, 3, 4, 5, 6. Yeah, I have 6 edges connecting 7 vertices. If I add another edge, that would automatically create a cycle, right? So doesn't that mean the minimum and the smallest would be the same? What do you know? Notice about the number of edges in your examples above? Is this a coincidence? The number in both cases is 6. One very useful and common approach to studying graph theory is to restrict your focus to graphs of a particular kind. For example, you could try to really understand just complete graphs or just bipartite graphs instead of trying to understand all graphs in general. That is what we are going to do now, looking at trees. Hopefully, by the end of this section, we will have a better understanding of this class of graph and also understand why it is important enough to warrant its own section. A tree is a connected graph containing no cycles. Sometimes this is referred to as a tree is an acyclic connected graph. Acyclic is just a fancy word for connecting no cycles. A forest is a graph containing no cycles. Now that this means that a connected forest is a tree. Oh, so a forest could be like a forest may not be connected. So we have this. So in this example, yeah, this could be a forest. Connect here, connect with these two. We have a forest because it's not connected. Does the definition above agree with your intuition for what graphs we should call trees? Try thinking of examples of trees. Make sure they satisfy the definition. In anthropology, you might study family trees like the one below. You might have also seen something called a decision tree, such as an algorithm for deciding whether a series converges or diverges. Sometimes these two contain cycles, as the decision for one node might lead you back to a previous step. Both the examples of trees above also have another feature worth mentioning. There is a clear order to the vertices in the tree. The definition of a tree does not include this added structure. Although we can impose such a structure by considering rooted trees, where we simply designate one vertex as the root. We'll consider such trees in more detail later in this section. Take out a piece of paper and draw it vertices in the circle. We are going to we are going to we are going to add edges to this graph following some requirements. First, add the fewest number of edges possible so that the resulting graph is connected. Okay, so I'll just start from here, connect them in a circle all the way till here, all the way, making a loop. That is, there must be a path between any pair of vertices. How many edges are in the graph you drew? So they said 8 vertices, right? One, 1, 2, 3, 4, 5, 6, 7, 8. Yeah, so there are 8 edges. Was the resulting graph you found a tree? No, the graph contains a cycle. Oh, sorry, wait. Hold on. One, two, three, four, five, six, seven, eight. Eight vertices. And then the edges is here. Now it's a connected graph containing no cycles. So yes, since the graph is connected and contains no cycle, it is a tree. Now start over with an empty graph again. This time add the largest number of edges possible so that the resulting graph contains no cycles. It will be the same thing. How many edges are in the graph you drew? But was the resulting graph you found a tree? Yes, since the graph is connected and contains no cycle. Where is the answer? How many edges? Seven edges. It is a tree. Seven edges again. It is also a tree. We wish to really understand trees. This means we should discover properties of trees, what makes them special and what is special about them. A tree is a connected graph with no cycles. Is there anything else we can say? It would be nice to have other equivalent conditions for a graph to be a tree. That is, we would like to know whether there are any graph theoretic properties that all trees have, and perhaps even that only trees have. To get a feel for the sorts of things we can say, we will consider three propositions about trees. So, our first proposition gives an alternate definition. A graph T is a tree if and only if between every pair of distinct vertices of T there is a unique path. Hold on. Yeah, it shouldn't contain any cycles, right? This is if and only if statement, so we must prove two implications. We start by proving that if a tree, if T is a tree, then between every pair of distinct vertices there is a unique path. Yeah, I'll just skip this. The existence of paths, the uniqueness of paths. Notice that both direction had two paths: the existence of paths and the uniqueness of paths. In this case, these two paths were really separate. In fact, if we just consider graphs with no cycle, then we could still do the paths of the proofs just that explore the uniqueness of path between vertices. A graph F is a forest if and only if any pair of vertices in F there is at most one path. So maybe there may be zero path, one path, but not more than one. So it contains zero path or one path. Any tree with at least two vertices has at least two vertices of degree 1. Any tree with two vertices has at least two vertices of degree 1. Yeah, that also. Okay, yeah, I understand. Because one of them has to be a starting point and one of them has to be an exit point. Because the middle vertices can't have only one. So this has a degree of 1, this has a degree of 1. There are two vertices with degree 1. So if I have it, I can represent the tree like this. And here, 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 and end. So these vertices over here has only, this is also a vertex. These vertices have a degree of 1, but no matter how many more edges I add, the vertices like the leaf vertices at the end, they will have only degree of 1, right? Yeah, so if there are two, there are only two vertices. Both of them are degree 1, more than two. These two have degree 1 and so on. So there will be at least two vertices of degree 1. Any tree with at least two vertices has at least two vertices of degree 1. Let T be a tree with V vertices and E edges. Then edges is equal to vertices minus 1. And 2, 3, 4, 5, 6, 7, 8 vertices. 1, 2, 3, 4, 5, 6, 7 edges. Yeah, yeah. So the edges is 1 less than vertices. It proved that this proposition is true for all possible values of V more than 1. Now that if V was 1, then the tree must have 0 edges. So yes, E is equal to V minus 1. We could then look at the trees with V is equal to 2 vertices. It is only 1 and it has E is equal to 1 edges. And then all trees with V is equal to 3 and then V is equal to 4 and so on. But that would take forever. Instead, we could do a version of proof by contradiction called the minimal criminal. We will assume that the proposition is not true. This means that there is some smallest tree for which it isn't true. If this smallest counterexample has p vertices, then we are guaranteed that all trees with v minus 1 vertices are not counterexamples. Let's see how this works out. Suppose for the sake of contradiction uh, that the proposition is true for all trees. Let T be a tree for which the proposition is true with the smallest number of vertices among all the counted example. Let V be this number of vertices of T. Since the only tree with one vertex has zero edges, uh, wait, what? Since the only tree with one vertex has zero edges. Okay, okay. Yeah, yeah, I understand. The tree has one vertex only, then there are no edges. The only tree with okay, okay. That cannot be our tree T. So we can assume V is more than 2. In particular, we know by proposition 2.2.4 that T must contain at least one vertex of degree 1. We call that V naught. Let T apostrophe be the tree resulting from removing V naught from T. Since we are removing a leaf, T naught is still a tree. The unique paths between the pair of vertices in T apostrophe are the same as the unique paths between them in T. Now T apostrophe has V minus 1 vertices. Since T was the smallest tree for which the proposition isn't true, we know that the proposition is true for T apostrophe. So T apostrophe must have one fewer edges than vertices. That is, T apostrophe has V minus 2 edges, but T has one more edge than T apostrophe, so it has V minus 1 edges. This contradicts our assumption that T does not satisfy the proposition, which completes our proof. One of the advantage of trees is that they give us a few simple ways to travel through the vertices. If a connected graph is not a tree, wait, what? If a connected graph is not a tree, then we can still use some traversal algorithm to find a subgraph that is a tree. Okay, okay. So if you have something like this, it's a graph, but it's not a tree because there's a cycle. Then we can have some traversal algorithm to identify a subgraph that is a tree. First, we should consider if this even makes sense. Given any connected graph G, will there always be a subgraph that is a tree? Well, that is actually too easy. You could just take a single vertex of G. If we want to use the subgraph to tell us how to visit all vertices, then we want our subgraph to include all of the vertices. We call such a tree a spanning tree. Given a connected graph G, a spanning tree of G is a subgraph of G, which is a tree and includes all vertices of G. Spanning tree of G. is a subgraph of G, which is a tree. Okay, okay, I see, I see. So, so if I take uh just this, 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 and this. If I take this subgraph, technically it's a tree, but it doesn't include all the vertices. Now, if I take another subgraph, which includes all vertices and edges except for this one right here, then that is a tree. Then that subgraph is a tree. That subgraph is called a spanning tree. So I can have one spanning tree. I can have one spanning tree that is like one spanning tree like this, or one spanning tree like this. One spanning tree like this. It includes all the vertices and edges. Nice. Turns out that every connected graph has one. Every connected graph has a spanning tree. Okay. Although we may not consider this in detail, to weighted graphs. Find two different spanning trees of the graph. So we have one here, 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 and then this goes separately, or we can like reverse it in here, 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 and then this branches out separately. This is a strange tree. Although we will not consider this in detail, these algorithms are usually applied to weighted graphs. Here, every edge has some weight or cost assigned to it. The goal is to find a spanning tree that has the smallest possible combined weight. Such a tree is called a minimum spanning tree. Finding the minimum spanning tree uses basically the same algorithms as we described above. But when picking an edge to add, you always pick the smallest. Or when removing an edge, you always remove the largest. What is this now? Rooted trees. So far, we have thought of trees only as a particular kind of graph. However, it is also often useful to add additional structure to trees to help solve problems. Data is often structured like a tree. This book, for example, has a tree structure, the vertex for the book itself, then raw vertices for each chapter connected to the book vertex, and so on. As soon as one vertex of the tree is designated as the root, then every other vertex on the tree can be characterized by its position relative to the root. This works because there is a unique path between any two vertices in the tree. So from any vertex, you can travel back to the root in exactly one way. This also allows us to describe how distinct vertices in a rooted tree are related. If two vertices are adjacent, we'll say one of them is a parent of the other, which is called the child of the parent. Of the two, the parent is the vertex that is closer to the root. Thus, the root of the tree is a parent, but is not the child of any vertex. Not surprisingly, the child of a vertex is called the grandchild of the vertex. We say that a vertex V is a descendant of a vertex V provided U is a vertex on the path from V to the root. Then we would call U an ancestor of V. Wait, vertex V is a descendant of a vertex U provided U is a vertex on the path from V to the root. Okay, okay, I see, I see. So suppose we have a tree. Okay, we have this tree over here. This one we will call U. Actually, let's call this one U and let's call this one V, and this is the root. Going from V to the root, the V comes in between. So V is and then we call U an ancestor. Wait. No, I flipped it. Should be V here, U there. V here, U there. So going from V to R, U is in the middle. So V is a descendant of U, and U is the ancestor of V. For most trees, there will be pairs of vertices next to which is a descendant of the other. We might call these cousins or siblings. In fact, vertices U and V are called siblings, provided they have the same parent. Note that siblings are never adjacent. Oh, yeah. Siblings are like on the same level and they have the same parent. Consider the tree below. If we designate vertex F as the root, then E, H, I are the children of F, E, H, I, and are siblings of each other. Among the other things we can say are that A is a child of C and a descendant of F. The vertex G is a descendant of F. In fact, is a grandchild of F. Vertices G and D are siblings. Okay. So they have a common parent E. Notice how this changes if we pick a different vertex for the root. If A is the root, then the lone child, then its lone child is C. A is the root, C is the only child, and then B, E, D are siblings. And then B, D are lone child, F and G are siblings, and then H and I are siblings. All of this flowery language helps us describe how to navigate through a tree. Traversing a tree, visiting each vector in some order is a key step in many algorithms. Even if the tree is not rooted, we can always form a rooted tree by picking any vertex as the root. The key to how we partitioned the tree in the example was to know which vertex to assign to a set next. We chose to visit all vertices in the same generation before any vertices of the next generation. This is usually called breadth first search. In contrast, we could also have partitioned the tree in a different order. Start with the root, put it in A, then look for one child of the root to put in B, then find a child of that vertex into A, then find its child into B. Okay, so on. As we travel as far from the root as fast as possible, then backtrack until we can move forward again. This is called depth first search. Okay, so breadth first search is like we start this, we search these two, and then we search these three, then we search this. No, wait, I'm wrong. Breadth first is like, so depth first is like you going deep, and then you go one level back over here, and then you go as deep as possible, and then one level back here. Back. And you go here, back here, back, go as deep as possible. I think you go leftmost first, right? Go as deep as possible, and then back, go as deep as possible, and then back here. And then back, visit it, and then you go here. I think for the first search, you go the left side first, right? And then for breadth, you visit this, you visit both the children, and then the children, and then these children, and then these children. The ordering of the visits are different. We chose to visit all vertices in the same generation before any vertices of the next generation. This is usually called breadth first search. Okay. So if we want to visit all the vertices, we can visit these two, and then these two, and then these two. We are not visiting V until all the children of U, both the children of U are explored. Yeah, there could be multiple children as well. What I drew here is never mind. Anyways, yeah, if we are exploring all the children before going down the next generation, it's this is called breadth first. Uh, Another way, look for one child of the root to put in B, then find a child of that vertex into A, then find its child into B, and so on. When you get to a vertex with no children, retreat to its parent. Okay. So go down, 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 down. You visited this. This has no children. You go up. Now go to the one you didn't visit and then keep going deeper and deeper. This is called depth first search. Okay, this was a small stream. I'm going to end the stream here and then I have to go somewhere and then I will come back. The next topic is about planar graphs. Okay, I will end the stream here. This was a small stream. And yeah, I'll see you guys next time. Bye.